Hello class, Dr. Yeager here. Today we're going to start with chapter 1 in the book, and just a basic review of the Earth itself, and certainly all things that we've been exposed to before in Earth science classes. And so let's run through it. We won't go through everything that the book covers, but we will hit some of the important stuff and things that I've found in the past students maybe need some refreshing on. So to get started, the Earth itself, when we look at Google Earth, we see this big flat sphere, and that's wrong in two cases. One, it's wrong that it looks flat and smooth on the outside, but it's not smooth at all. We certainly all understand that the surface of the Earth is not flat. There's all kinds of change in terrain from place to place. There are high points and low points. We're probably aware that the highest point on the planet is Mount Everest, which is almost 30,000 feet above sea level. So if you were standing down on the beach in Corpus Christi, and I was standing on the top of Mount Everest, something which will never happen, but if that were the case, you obviously couldn't see me, but if we were to snap our fingers and then be right at the same place, only at the same elevation, I would be 6 miles, almost 6 miles above you, which would be really weird. But yeah, that's really, really high. There's lots and lots of really high mountains, and we're aware of that. And there are also lots and lots of low places. We generally sort of think about sea level as being the lowest place, but there are lots and lots of deep trenches underneath the ocean. The bottom of the sea is not a flat place either. The lowest point on the surface of the planet, or the deepest trench, the deepest area below sea level, is what's called the Mariana Trench, which is a subduction zone over in the Pacific Ocean near Asia, and it's really, really deep. It's deeper than the Mount Everest is tall, so 36,000 feet deep. So the surface of the Earth is definitely not flat. And when we look at Google Earth, Earth looks like a sphere, and it's actually not. It's what's called an oblate spheroid, which is a question that a lot of students end up missing on the test. I can promise you that one's going to be on there. All an oblate spheroid is it's almost a sphere, but oblate spheroids are spheres that are a little bit scrunched in on the top and a little bit bulged out in the middle, and so that means that the if you were to walk around the Earth at the equator and then walk around the Earth from the North Pole to the South Pole, that walk would be a little more short as you walked from North Pole to South Pole than it would be if you walked at the equator. The equator is bulged out because as the Earth spins on its axis, the momentum of the Earth itself as it moves causes it to bulge out. You've experienced this if you have ever been in a car that did donuts in a parking lot. If you're in the passenger side and the driver is doing donuts and you're going around and around and around, you felt the force of the movement of the car inside. It's called centripetal force. You felt that force push you out, and you were pushed up against the door if you weren't wearing your seatbelt. How dare you do donuts and not wear your seatbelt? But the same thing happens to the Earth, and that causes the Earth to push outward. Anyway, as the Earth pushes outward, it flattens down at the top and bottom. That's what an oblate spheroid is. The Earth moves at about a little over 1,000 miles per hour at the equator. And because the Earth is this oblate spheroid, that's the fastest place on Earth. So if you were standing on the equator, you would be moving with the Earth at 1,040 miles per hour. That number obviously gets shorter, or that number obviously gets slower as you travel away from the equator, because the the distance that you would travel as you went all the way around the world in one day gets less. And if you were standing at the equator, right, you're moving at that 1040 number. If you're standing here over the course of 24 hours, you're not going to go as fast because the Earth, because you wouldn't travel as far, right? If we just look at this line here, we pretend the Earth is two-dimensional. If we look at this line from here to here, this line is longer than this line from here to here, right? This latitude line up here is shorter. So as you get away from the equator, the speed of the Earth moving is actually getting slower. And if you're standing at the North Pole, which is up here, the South Pole down here, you're actually moving so slow that you are going to essentially not move any miles per hour, because all you would do is just turn around one day. You'd be like you would just stand in place and rotate around one time in 24 hours, which is really, really, really slow. One of the most important things that we need to take away from this chapter 1 is a refresher of latitude and longitude, because we will use latitude and longitude a lot this semester. And we need to be able to understand what it means. You'll use it a lot in Google Earth, and I'll show you here in a few minutes. Google Earth is a great place to play with latitude and longitude. I'm going to post another video I made at a college I used to work at that will really go into the details on latitude and longitude, but I'll just basically sort of explain it right here. Latitude and longitude is a way of defining places using numbers on the planet. And if we have two numbers, a latitude number, which tells us how far to the north or the south something is from the equator, and a longitude number, which is a number that tells us how far something is to the east and the west of this line over here called the prime meridian. If we have those two numbers, we can tell where any place is on the planet. Really, really specifically and really precisely. You got to have both numbers. If you only have a latitude number and you only have a longitude number, you're not going to be terribly precise. But if you have both of them, you can be really, really precise. So let's look at latitudes first. Latitudes are a number that tells us how far to the north or the south something is from the equator. So the equator, we all know what the equator is. The equator is this imaginary line that cuts the Earth into two equal halves, okay? And since the equator cuts the Earth into two equal halves, we have a north value and a south value for longitude. There are five important lines or what we call parallels of latitude, and these parallels of latitude are the equator, the North Pole, the South Pole, and then we have a tropic of Cancer and a tropic of Capricorn in the southern hemisphere. The tropic of Cancer is in the northern hemisphere. We'll talk about those become really important when we start talking about weather. Each of these has a mathematical value or a number value associated with it, and they have a number associated with it because what we're really talking about here is the geometry the geometry of a sphere, or in this case, because we're only talking about latitude, the geometry of a circle. If you remember from geometry class, there are 360 degrees in a circle, and that's the number that we will use to give us our latitude value. Since we always start at the equator, our mathematical value for the equator is 0. The mathematical value at the North Pole is 90. Okay, it's 90 to the north. We always have to say to the north or the south. If we just say 90, we don't know if we're talking about the North or the South Pole. Okay, so the mathematical value of the equator is 0, and it's 90 at the North Pole. What we will find if we were at the equator and we started walking to the North Pole, we started at 0 degrees latitude and walked, our location would go up as we got away from the equator, the latitude value would get greater and greater and greater until we got to the North Pole, where we would be at 90 degrees north latitude. As we started going back down towards the equator, we would be getting closer to the equator, right? So we would be moving back down from 90 towards 0. On the other side of the world here, when we cross the equator, we'd be back at 0. And as we walk towards the South Pole, we would get closer to 90 degrees to the south. Then as we kept walking towards the equator again, we would get back to 0. So what you find is that if we start at the equator and we walk all the way around the world, we walk 90 degrees, and then from the North Pole to the equator again is another 90 degrees, and then from the equator to the South Pole is 90 degrees, and so on. So that accounts for all 360 degrees, okay? Now that latitude value tells you how far to the north or south something is, but that value by itself won't allow you to be very precise in finding a location. We need to have a second number that tells us east or west, and that value is the value of longitude. Essentially, longitude works the same way as latitude. The difference is the starting point. It makes sense to start from the equator, because when you're going to cut the Earth in half into a north half and a south half, like here, there's only one place you can do it. You can only cut the Earth into two equal halves at the equator, right? If we were making up our own latitude and longitude system, it wouldn't make sense to do it way up here, would it? Because then you would have two unequal parts. You would have a small northern part and a really big southern part. That wouldn't make any sense. So it makes sense to use the equator to start with. It's a little different with longitude, because we could start anywhere. There are an infinite number of lines we could draw that go through the North Pole and the South Pole and cut the Earth into an east half and a west half. So the line that was chosen as the starting point for longitude starts at the North Pole, comes down, it goes through London, England, and then it goes down, crosses the equator right about here, and goes down to the South Pole, and then comes back around. That's called the prime meridian. And it starts. That's the equivalent of the equator in terms of longitude. Okay. Now, just to make things complicated, we do things a little bit different with longitude. If we were going to start if we were on the equator and we were going to start at the equator and start walking to the east, there's no, since the prime meridian is kind of an arbitrary line. There is no quarter of the way line that makes sense to stop at. So if we were starting at the equator and we were going to walk to the west, we would just keep walking. And as we got away from the prime meridian, our longitude value would get bigger and bigger and bigger and bigger and bigger. Until we got all the way around, halfway around the world, we would pass 90 degrees to the west, and we would keep going. Unlike latitude, our longitude value can be greater than 90. Our latitude value can't be greater than 90. So we would get all the way halfway around the world at the equator there, and we would have traveled halfway around the world. And since we're dealing with 360 degrees, we would have traveled 180 degrees. Okay. At that point, if we kept walking, we would be at 180 degrees. And as we got back closer to the prime meridian, our longitude value would go down. If you have not played with anything like this in a long time, this is going to be maybe a little different for you. And you're going to have to play around with it. You're going to have to work on it. This is not something that you're just going to be able to read the chapter once and figure it out. You're going to have to practice it a little bit, okay? So let me show you how to practice this on Google Earth. You go to Google Earth up here at the top. You go to View. Okay, you click on View, and then you go down and you click on Grid. When you click on Grid, boom, 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 latitude and longitude will automatically pop up on your screen. What the best thing to do and the easiest thing to do is to just look around, get a get a handle on, figure out how this works. Playing with it is the best way to, playing with it is actually the best way to get it into your head. We'll stop there. We will pick it up next time, and we will see you then.